In this video, we want to talk about how to creating new functions out of old functions. Now, the first thing you need from this is to have done the parent function. So if you haven't gone through the parent function worksheet or watched the video on that, or if you're unfamiliar with those, go back and look at that before we go forward. Now, what we want to look at is if we start with one of those parent functions, let's say x squared, how would that function change if we want x squared plus 2? Or the quantity x plus 2 squared? How does that transform our basic parent function? And we have seen this before in pre-calculus, that we know if it's a plus or minus outside the function, it moves it up or down. And if it's a plus or minus inside the function, it moves it left or right. And if it's plus 2, it moves it to the left 2. So we want to combine that idea with our parent function idea. So as I said, if it's a plus or a minus outside the function, we move up or down. If it's inside, it goes left or right. So if we look at an example here of this function, if this is our f of x, and we want to look at f of x minus 2, what that's going to do is to take our shape that we start with, and we're going to move it to the right 2. 1, 2. Because it's inside. And remember, the sign changes. If we have our basic shape here, and we have x plus 1 inside the function, this moves it to the left 1. And then minus 2 is going to move it down 2. So we get from this shape to this shape by sliding it over. The other things we can deal with are reflections. A negative inside is a reflection over the y-axis. A negative outside is a reflection over the x-axis. So if we look at an example here, if this is our basic shape, let me move it over to here, and we have a negative inside, the negative inside flips it over the y-axis. So what that's going to do is it's going to take this shape and just flip it over the y-axis so it looks like that. Ooh, draw a straight line. If we take this shape down here and we want to flip it over the x-axis, that is going to take the part up here and down, and this part here, and flip it over like that. So inside a function is the y-axis, outside the function is the x-axis. So if we combine all this with our parent functions, and we have seen this before, if we had x minus 3 quantity squared minus 1, that is our parabola, but it's going to be moved right 3, down 1 to there, and then we get our parabola. E to the x, x minus 2 inside, which is going to be normally our e to the x goes like this. We're going to move it right 2. So instead of going through a 1 there, it's going to go through there. And we get a shape like that. So this is combining our parent functions and our transformation of functions. Now, as we talk about graphing functions, there's a couple different ways you can graph functions. One we just looked at by using transformations of our basic parent functions. And part of graphing functions is just your drawing skills. How well can you draw a function with your pencil? Whether you know what it is, one of our parent functions, or if you're trying to draw something, plotting points or whatever it is, on something that you don't know. Now, some other things that deal with graphing functions is when you use our calculator. And just because you type it in the calculator and get your answer doesn't mean you're done and whatever the calculator says is your answer. So let's look at a few other things we got to consider. One, is the graph reasonable? So that means when you hit graph and you hit the graph, is this window reasonable? Does it make sense? Can you see all the important characteristics? As you look at the calculator window here, can you see everything about the graph you need to see? Or do you only see part of it because your graph doesn't make sense, right? You should have some idea of what the graph should look like before you hit graph, so that when you look at it, you can say, okay, that looks right, or that's not right. Third thing you need to be able to do is you need to be able to interpret what you're seeing. Are points maxes? Are they points mins? Are there asymptotes? What's going on with the graph you're looking at? So you notice a lot of these are not your ability to draw something. It's your ability to view and see and understand what the calculator is doing. And the final one we have here on the calculator is we have to recognize when the calculator makes a mistake, or recognize what's going on the calculator so that we can really interpret what's happening. So let me give you a couple examples. First off, let's look at this one. 1 over the square root of x squared minus 2. Now, if we think about the domain, what's on the bottom can't be negative, right? Can't be 0. So if we think of x squared minus 2, and we say, okay, where is that going to be 0? That is at plus or minus square root of 2. And if we pick numbers bigger than square root of 2, it works. Less than, it doesn't. So my domain is negative infinity to negative square root of 2, union square root of 2 to infinity. So now let's graph this on the calculator and see what we get. So I already have it typed in here. We do that. And now let's graph. So there is the graph. Now the question is, what's happening here? So we saw our domain was negative infinity to negative square root of 2. Remember, square root of 2 is about 1.414. So that looks pretty close right here, 1.4. So it's from negative infinity to negative square root of 2 and square root of 2 to infinity. But how high does it go? Does it just stop? It looks like at about 2. Well, let's zoom in. Let's see if we can figure out some better characteristics. So let's go to 4. Okay, that looks still pretty similar. Only goes to 2. Let's zoom in a little bit more. I'm going to go from negative 2 to 2 for my x's. And we'll let the y's go up higher. Before, it only went up to 2. Now it's off the graph. So let's see how high this goes up. Let's go up to maybe 10. And I'm just kind of guessing these and trying to figure it out. And there it stops. You can see now it's at 1, 2, 3, 4, 5, 6. This goes up to 6. And what's really happening here, even though it's hard to see, what's happening here is we have vertical asymptotes here. And our graph goes up forever. Now, that's hard to see without kind of zooming in and figuring it out. That's part of interpreting or understanding what the calculator shows us. Even though it appears to stop, it really doesn't stop. Let's look at another one. X to the 201 raised to the 1 over 201. Now, first off, if we just use our algebra here, we know when we have this, we multiply these, and this should be just x. Algebraically, this should just be the graph of y equals x. That's one of our parent functions, straight line, right? Well, let's look at what happens. So if we go in here, let's turn this one off, turn this graph on, we get that. It stops. Let's zoom in a little bit, see if we get any better view. What is happening? Well, let's hit the trace. Down here, it's saying our graph is 0. That doesn't make sense. And then if we go a little bit more, up here, it works. Y equals X. And then if we go higher, it dies again. Why is that? Well, here's the reason. If we look at our function, x to the 201 to the 1 over 201, what happens is if I take 2 raised to the 201, I get a gigantic number. But if I take 3 to the 201, and I'm not sure exactly where this is going to occur, that's still okay. What if I take 3.5 to the 201? I get an overflow. So what happens in my graph is once I get past 1, 2, 3.5, 3.2, then this first part gets so big, the calculator blows up before it ever gets to the second part, even though algebraically it would simplify. Likewise, if we take a small number, 0.2 to the 201, we get 0. Now, is that 0? Of course not. But it's so small, the calculator thinks it's 0. So for these small numbers in the middle, it just assumes it's 0 because it can't handle the numbers and doing the calculations. The calculator doesn't do algebra. It just does this arithmetic with the numbers. So those are examples of things that mess up the calculator, that we have to understand what the calculator is doing for us to truly grasp what's going on. We want to look at a few more things that we've talked about previously as functions. And the first is piecewise functions. Now, if you remember piecewise functions, these are functions where we have two parts, two pieces, that each are defined. So if we look at the line 3x plus 1, that would be a y-intercept of 1, slope of 3. And if I graph this line, I would get this graph. However, this function is only defined when x is less than 0. So if I think of my x's here, here is 0. All of these over here are when x is positive, so I get rid of these. Here, this is then an open circle. The second is 2 minus x. So this is a y-intercept of 2. Slope is -1. And this is when x is greater than or equal to 0. So I have a dot there. And I get the graph going this way. So there's my piecewise function. Know that this still passes the vertical line test. When you do this, you should still be able to pass the vertical line through the graph and only intersect one point. So another way to do this is to try to find the formula for a piecewise function. So to do this, we can see there's 3 parts. So the first thing I'm going to do is find the domain of the 3 parts. The first part is from -1 to 0. That's this piece. The second piece is from 0 to 2, parentheses. And the third piece is from 2 to 5. So next we need to find, I'll use some color here, we need to find the equation. We'll do the easy ones first. The equation of this. That's just a horizontal line at 2. This is a horizontal line at 1. And the last one, we need to find the equation of this. Well, the slope of that line is 1, so that's 1x, plus the y-intercept is 1. So there is our piecewise function that explains this graph. Now, one function that we're familiar with is the absolute value. So we've seen the function, it's one of our parent functions, absolute value of x. And many times we think of the absolute value of x as just make it positive. But when we do some algebraic things in calculus, we need a better way of defining absolute value. So here's how we're going to define it. We're going to say if x is greater than or equal to 0, the absolute value is x. If x is less than 0, it is equal to negative x. Now, first, that doesn't quite make sense. But let's look at it here. If I would say, what is f of 3? If you put 3 in, 3 is greater than 0, so it's just 3. If I say, what is negative 3? That is less than 0. It is minus x, so that would be minus a negative 3, which is just 3. And if we look at the graph, we could see when it's greater than 0, it's just x. When it's less than 0, it's negative x, and we get our V shape of our absolute value. So that's a way to write the absolute value really as a piecewise function. And the last thing we want to talk about here is composition of functions. And if you remember, the composition of functions is this little circle, this f of g. And what the composition of functions mean is this is f of g of 2. So you remember, you start on the right and you take the 2 and you plug it into g. That's g of 2. So if I put 2 in here, that's 5. Then I take that answer and I put that answer into f. So I put 5 into f and I get 11. If we do it with an x, this is g of f of x. So this is g of the whole function. So g of 3x minus 4. And then if I put that in, I would get 3x minus 4 squared plus 1. And then if we multiplied that out, we would get 9x squared minus 24x and plus 17. So that's what this composition means. It means putting one function inside of another function. Now, one of the ways we're going to use it a lot in calculus is actually going the opposite way. So we given a function, cosine squared of 3x, and we want to write this as f of g of h. So what to think of is this is the inside. You take h and you put it into g. You take that and you put it into f. So f is all the way on the outside. So we start with h. What's the insidemost function? And that would be 3x. Now it's a little bit hard here to see which one is it, cosine or the squared. So I'm going to rewrite this like this. If we can recognize that cosine of 3x squared, that really is the same thing. We put this 2 here, but we could put it on the outside. Then that helps us see that g is cosine of x and f is x squared. So if you put h into cosine and put all of that into x squared, that is how you can get this function. All right, we are done with section 1.3. You're able to do all of the homework for that section.